Okay, today I'm gonna start to talk about signal processing and the, uh, the steps that we need to take in order to analyze the signal. Um, Before I go ahead and talk about the signal processing, let's just very quickly see why we need to do the signal processing. In general, when if you want to say what is the signal or what we're talking about the signal, um, usually any type of the signal that we have that contain information, we may need to do sometimes the types of analysis on that in order that we can either gain the data that the signal has, or sometimes manipulate the information in the signal. And if you look around, it's almost in every things that we use, somehow the signal processing involved. For example, the very first example is the cell phone we are using. Almost everything that the cell phone does uh, involves some types of signal processing. For example, it capture your voice and then transmit it over uh, uh, antenna, and then it receive the signal from the other party and then convert that to the voice that you can hear that all those things. Or for example, you take a photo, it's the photo goes through lots of signal processing before you actually uh, see that. In As I said, there are lots of things around you. If you look at it, for example, if you send an explorer to the space, that any information that the explorer sends back to the earth is going to be in form of signal, and then you have to go back and look at those signals to see what information are sent to you. Or if you go near the beach and look at the waves that are in the ocean, you can see all those waves. Is basically some kind of signals that you can see them, they're changing, and then by analyzing those signals you can get some information about the wave field you have in the ocean or the sea. If you go to the doctor, majority of the thing is imaging the doctor does involve some kind of signal processing. For example, if they um, uh, get the signal of the heartbeat and they give it to the doctor, so doctor sees all the, for example, heart, the health of, evaluate the health of the heart, or they, for example, they may take some um, um, signals from the brain to evaluate it, or do some imaging, or those kind of things involve the signal processing um, that we are working with them. Usually, when we are talking about the signal processing, simply we will see something like that, that we have, for example, if we say whatever value we are having, any value that it can be, and then it's going to be, mm, mm, uh, for example, changed or measured over time. So that value might be, for example, the voltage, it can be the current, it might be the wave height, it can be the, for example, the light intensity, anything that's here, and then you will see how it's going to change over the time, and then you usually get some kind of signal, something like that, and then you try to look at that and see how that signal, what types of information that signal uh, has it. And as I said, sometimes you want to gain the information, sometimes you want to manipulate whatever information is in there. For example, you're using your cell phone and you talk over cell phone, and then your cell phone is gonna take your voice, but when it's gonna the mic of the mic is gonna take your voice, but it's also gonna contain the background voice, and then you want to remove the background voice. So before you're actually the voice, your voice is gonna be sent over the antenna. The phone might do some signal processing in order just to remove the background noise, only keep your voice, and then send it um, there. So either we want to see what kind of information that, or we want to do some manipulation on whatever information that signal has. So we will have to go through some signal processing um, for that purpose. Usually, when we are talking about the signal, generally we are talking about something that change over the time, but it can also change over the space, over this something that have changing. For example, on if we change the distance, it might have some changing order. So, if, for example, the distance might have some kind of signal that is changing by the time that, for example, the distance changing. For example, if you go on the beach and stare at one area at one point and just look at what happened at that one point, basically you're not changing the location, you will see the water goes up and down. So you see the effect of the wave at that point over the time. So nothing changed, but only you see the water at that specific point goes up and down over the time. But if you look up and look at the entire, for example, sea in front of you, then you will see that not only the wave change over the time, also by looking from point to point, you will see that the wave in the ocean change. So it can change in the time, it can change over for example, distance, and sometimes it can change for both. So when you're looking at the wave field in the ocean, or you're standing by the beach and look at it, both of them changing. The wave field in the ocean change over the time. Also, if change over the distance by just turning your head around, you will see it's changing. So, but for simplicity, we are at this point we only stick to the condition that whatever signal we are looking at, that um, it's only changing over the time. We assume it's not changing over the space, only it's changed over the time, and we want to see how we can analyze that. When we want to analyze, as you see, if you only stick to this one, um, what the signal we have here is in the time domain. And this one is in a space domain, and we may have it in time and space domain. But if we just stick to this one, so the signal we have in time domain, and when we say we want to analyze the signal, we may want to analyze the signal in time domain. Sometimes it's easier that bring that into the frequency domain and then analyze that signal. So if I go ahead and say, okay, this is the signal I have here, and this signal is whatever as a function of time, then I would say sometimes, and I will show that if I can bring that, convert it from the time domain into whatever I'm looking at into the frequency domain. So instead of having something like that, convert it into frequency domain, and then have, for example, some form of, for example, signal like this, and they say, okay, I'm gonna analyze that instead of time domain into the frequency domain. So we may be able to analyze the signal in time domain. We may be better to analyze it in the frequency domain in order to uh, uh, find out what is happening. Now, see here, this is, and while we are bringing it into the frequency domain, it's usually much easier to work with the signal in the frequency domain rather than in the time domain. So that's why we are bringing it to frequency domain, and you will see later why it's much easier to work with that. The very common method that you will see to bring the signal from frequency domain, from the time domain to the frequency domain, uh, is to use the uh, Fourier transform or Fourier analysis. So So write it. So here um, transform. I will not go in detail that what is the Fourier transform is that, rather I want to go through the concepts of how we can use the Fourier transform to bring the signal from time domain to the frequency domain, and why it's easier to bring the signal from time domain to frequency domain rather than dealing with that in the time domain. Although it's not always true, but generally it is like that. It's much easier to work with that in the frequency domain. Now I'm gonna give you some walk you through that why it's important. So assume I have a some wave. Assume I have, for example, um, so assume whatever signal I'm measuring here over the time. So assume I have three of them. So I have three signals measured over the time, like this. So assume it's a V1, it's a V2, and it's a V3. So I assume I measured three signals over the time, and assume there are sinusoidal signals. So assume I have the first signal I measured is look like that. The second signal I measured is look like this, and the third signal I measured is look like, for example, something like that. So some sinusoidal wave, something like that. So assume I measured three signals similar to that. No, let's just say if I add these signals together, what happens if I go say, okay, this one plus this one plus this one is gonna be equal to something. So I just add them to see what I get. And as I said, assume, so I'm gonna have this as again time, and it's gonna be the V, that the V is gonna be V1 plus V2 plus V3. So I'm gonna simply add these three together here. So if I add them together, assume I'm gonna get something like that. I don't know what I get, but I just something hypothetically. So assume I'm gonna I get something like this. So assume if I add these three, this is what I'm gonna get. Now look at this one. So I can say that if I add three sinusoidal waves, so all of them are sinusoidal waves. They're simple wave. So I can say the V1 is, for example, what is it? The amplitude, the cosine omega t. Then the second also the cosine wave, also cosine. So I have three cosine wave, and then I add them, I will get this one. Okay. Now let's look at the other way around. Now if I assume I have this signal here, so assume I have that right here. So assume I have a signal. That's gonna be, so that's gonna be a V over time, and I know that signal is like this. Assume I have this signal, and somehow I can find a way to break it down to three signals. So I can find this and get it. So I say, okay, I'm gonna break it into three sinusoidal wave of V1, V2, and V3 in a way that if this is again, it's the time, the time, in a way that if I add these three, it's going to give me the original one. So if I find a way that I can break it or decompose it to, as I said, three signal, that's going to gives me this original signal to be like that. So let me do that again. So assume I can break, if I can find a way that break the signal in these three signals. So if I can do that, what I have here, I just know it's some kind of FT. I don't know what it is. So I cannot write it in any way, but I know it's some kind of FT here. But here I have three sinusoidal waves. So if I go ahead and say, for example, this distance here is A1. So it's going to assume it's going to be A1, and assume that this one is going to be, this distance is going to be A. So it's the amplitude of each of the wave, and this distance here is going to be A3. And assume it has a frequency of F1. This one has a frequency of F2, and this one has a frequency of F3. So I can write it here. What I can write here, I can say that, okay, this one, the V1, is A1. Assume it's a cosine wave, so it's going to be the cosine omega. So omega 1t plus theta 1. Also, I can write this one at the same. So V2 is A2 cosine omega 2t plus theta 2. And the V3 is the A3 cosine omega 3 plus theta 3. So assume I can write, so I can write this as a, because these are a cosine wave, so I can write it as this, and so I know that also the omega, I'm just gonna write it here somewhere up here. So I know the omega is 2pf. So I know it's a frequency. So I can have omega 1, omega 2, omega 3 for each of them, and the amplitude of the first one, second one. Now whatever I have here is that ft, the v is equal to ft. I can say that ft, whatever it is equal to this first sinusoidal wave plus this second sinusoidal wave plus this third sinusoidal. So I can, instead of whatever I have here, which I don't know what it is, I can go ahead and write it in this one and say, okay, ft is equal v1 plus v2 plus v3, or in other words, the vft is equal to a1 cosine omega t plus theta 1 plus a2 cosine omega t plus theta plus a3 cosine omega 3t plus theta 3. So in other words, I'm writing a signal in the time domain that I have no idea what is my equation, what formula can be used to present that equation in the time domain. Replace it with some summation of the sinusoidal wave. So up to this point is that now that I have this sinusoidal wave, usually it's really easy to work with this sinusoidal wave because then you can go and look at each of the sinusoidal wave, or if you want to make changes, you can go and change any of these sinusoidal wave or the same, or remove it, or whatever you want. So you can analyze it, you can study it, you can manipulate it in this way. While it's not much easier to do it here because it's FT that you don't know what it is. Um, Up to this point, I assume that I can go and if I have this, decompose it into this simple sinusoidal wave. But how I'm gonna do that? It's easy way, it's a good way of to present the function. But how I'm gonna break this into series of sinusoidal wave that if I add them together, it's gonna gives me the original signal I have. This is where the Fourier transform comes handy. So the Fourier transform basically says that, if I want to write it, is that if you have, and can write it for time versus, so I'm going to write it for the time. It says that if you have any function in a time, you can write it as a series of sinusoidal wave that goes from 1 to, you can say infinity or n, that doesn't matter. And then you have series of sinusoidal wave just added together. So it's going to be n omega n omega t plus bn uh, sine n omega t. And then the omega is again is 2pf, or it's going to be 2p, sorry, 2 pi divided by t. So in other words, it says that whatever function I have, I can add it into series of cosine and sine waves. How to get these? Usually we use the computer to the fast Fourier transform algorithm, FFT, in the computer to gives us these values for the Fourier transform. But it's usually like that. So it says that whatever function I have in a time domain, I can break it into series of cosine and sine wave that if I add them together, it's gonna give me the original one. Here, just to mention that there is one term we have here that is neither sine nor cosine. This is basically a mean in the signal. If your signal has a mean that is not zero, then you add them in. So if I go back here, I assume we have some sine and cosine. You see the mean of the sine and cosine, all of them are going to be zero. If the original signal has some mean value, the average value, so after we add all this cosine and sine together, then we are going to add the mean value to shift it, the entire function up or down to that mean value. So this term is basically represent the mean value, and the rest is the sine and cosine function that we have. Now let's go back to this simple example I have. So I said that my ft, assume I can write my this simple function as a ft as adding these three together. So I have these three sinusoidal wave together. So assume I only can write this specific function with cosine. I don't need any sine function. So if I go ahead and say, okay, my the v is v1 plus v2 plus v3, and then therefore I go ahead. So the v is ft, the function is time, and it goes says, okay, it's going to be the a1 cosine omega 1t plus theta 1 plus a2 cosine omega 2t plus theta 2 plus a3 cosine omega 3t plus theta 3. So I assume I can write this function into these three um, uh, cosine wave. Now look at each of these. Each of these function has the amplitude. So it has the amplitude. So it has the amplitude, amplitude, and amplitude. And each of them has its frequency. So if I come here, so it's the omega 1. So it basically is corresponding to the f1. So it's the omega 1 is 2p 2 pi f1. So it has same here. Omega 2 is 2 pi f2, and the same here. Omega 3 is 2 pi f3. So each of these, so I have three waves that if I add them together is going to generate the original wave, and each of them has an amplitude and frequency. Now let's look at what we have. So if I go back and here, so look at, this is what I have in the time domain. So I'm going to draw it again here. So in a time domain, I have something like this. So it's going to be in the time domain. It's going to be the V, and try to draw it the same as it is here, hopefully. So in the time domain, that's what I have. Does it look like, no, doesn't look like it. So assume this is in the time domain. So hopefully it's look like the one that we had. So it's ft. Now if I draw another plot, but this time instead of having it as a time, so if I draw a plot like that, and then plot like that, and this time I'm gonna draw this as a frequency, and this time is the amplitude, and then draw that here. So f1 is the largest one, so it's gonna be somewhere here. F2 is the smallest one, it's gonna be somewhere here, and F3 is gonna be the somewhere in the middle there. So it's gonna be F3. So it's just to make sure these are similarly corrected. So the F1, so F1 is this one. The F2 has the largest value somewhere here, and then F3 is sitting, so example, somewhere in the between of these two. So it's the F1, F2, and F3, and this is going to be the A3, and this is going to be the A2, and this is going to be the A1. So you can see that here, basically, we can say that, look at this graph. So I have the A as a function of the F. So I have three value here, one here, one here, and one here, which these three value basically represent this first term here, the second term here, and the third term here. And I know that if I add these three together, I'm going to get the original function. So this is what I have in the time domain, and I can go ahead and say, look at it. Instead of having it in the time domain, I can have it in the frequency domain. So the entire this signal, which contains maybe thousands of data points in the time, just converted to three data points in the frequency domain, 1, 2, and 3. So instead of going ahead and try to analyze all these data points here, I only can come here and say, okay, that's much easier. I have a plot with three data points, and let's deal with these three data points rather than going ahead and try to deal with this whatever number of data points I have in the original time series. So that's how we actually can convert these two together. So I can convert these to the time, from the time to the frequency domain, or convert back from frequency domain to the time domain. And depend on, as I said, what type of analysis we want to do. Sometimes it's much easier to do it in the frequency domain. Sometimes it's easier to do it in the time domain. So depend on that, we will come here, we will do it in the time domain. If it's easier to do it frequency, just convert it to the frequency domain. Otherwise, convert it back to time domain. So that's how we use the Fourier transform to bring whatever we have in the time domain to the frequency domain, or vice versa. If you have it in the frequency domain, we bring it back to the time domain to do the analysis. So that's the very basics of how we use the Fourier transform to go back and forth from the time domain to a frequency domain and vice versa.